In this film, we are going to measure the velocity of light. And then we are going to compare the speed of light in air and the speed of light in water. Light travels so fast that it was long thought to be instantaneous. And even after it was believed that light travels at a finite speed, it was centuries before men had devised equipment sufficiently precise to make a successful measurement. Actually, it was over a century ago that Fizeau made the first such measurement. And since that time, many other scientists have made successively more accurate measurements of this most famous physical constant, the velocity of light in air, approximately 300,000 kilometers per second. To measure such extraordinary speeds, special conditions are necessary. On the one hand, a measurement can be made using relatively simple timing devices if we employ extraordinarily long distances, astronomical distances, for example. This is what Raymer did in 1676 using the eclipses of the moons of Jupiter. On the other hand, we can use simple, convenient, relatively short distances, which can be accurately measured if we employ timing devices that are sufficiently delicate to measure very short time intervals, milliseconds, microseconds, or even small fractions of a microsecond. This precise and sensitive oscilloscope is just such a device, and it forms a key element in the first of our two experiments. With this electronic clock and this other equipment which you see grouped here, we went outside and made a quite satisfactory measurement of the speed of light. We went outdoors because we wanted a good-sized carry for our beam of light, yet one that was manageable. And we finally set up on a high school playground. We wanted a light path which was 300 meters long, because we know that light travels 300 meters in 1 microsecond. But we intended to fold our light path once, which meant that we had to set up where we had 150 meters of straight throw. This is the scheme which we used. Our light source was located at the focus of this parabolic mirror. It sent a beam of light in this direction to a plane mirror located at the far end of the field. This mirror folded our path and reflected it back to this parabolic mirror here with a photocell at its focus. And the photocell was connected to our timer. Now our aim was to measure the time of travel over a distance. But what we actually measured was the difference in time of travel over two distances, a short path and a long path. We arranged to catch a fragment of our light beam on a small mirror here, reflected across into another small mirror here, and off that into our receiving parabola. This gave us both a short light path and a long path. The light source placed in the focus of this parabolic mirror here was a spark gap pulsed by a 60-cycle alternating current. It was a first-class light source for our purpose, providing a rapid succession of very short light pulses. The oscilloscope, our electronic timer, was arranged to trigger on the receipt of a light pulse put out by the spark gap and picked up by our photocell. The short path performed the double function of triggering the oscilloscope and providing us with a first blip on the cathode ray tube. If this circle represents the face of the cathode ray tube, then the first blip might look like this. And the signal returning via the long path should then produce a second blip like this. If the difference in distance between the short and long paths is 300 meters, as nearly as we can measure it, then the time difference between our two blips should be almost exactly 1 microsecond. So we adjusted the duration of the sweep on the scope to be 2 microseconds. On the face of our scope, there is a scale. If the total duration of the sweep is 2 microseconds, then each major division should represent 2/10 of a microsecond, and we would expect 5 divisions between our two blips. To check that our oscilloscope was properly calibrated, we used a standard signal generator. With our plans complete and our equipment ready, we went out to the playground. We began by placing the distant plane mirror and then carefully measuring off 150 meters from it. The face of the plane mirror was vertical, and we were careful to run our measurement out normal to its surface. Small pegs made it easier for us to double-check our measurement. We marked the 150-meter point with a broad stake. We positioned the parabolic mirrors a short way beyond the measured distance, as we had planned. In the source mirror, we fixed a clear 150-watt bulb to help us with the alignment of our equipment. We checked to see that the bulb was properly in the focus of the parabola, and then we began the process of lining up the big mirrors. The first step was to place a white marker on the line of sight between the source and the plane mirror. Then we adjusted the parabolic mirror until the beam was lined up on the marker. We found that very small movements of the tripod legs shifted the beam through a considerable arc. We had to carry out a similar maneuver at 4 or 5 distances, each one further away, to guide the beam of light both horizontally and vertically directly into the distant plane mirror. A small adjustment on the distant mirror then brought the beam back into the receiving parabolic mirror. If we were really getting our beam of light back here, we ought to have a bright trace show up on our translucent screen at the focus of the receiving parabola. We placed the short path mirrors carefully to ensure that the difference between the short and long paths was just 300 meters. We found that we could use quite small mirrors at this close range to produce a return image similar in intensity to the one coming back on the long path. When we had both images coming in well, we had carried our lining up as far as we could in daylight. All that remained to do before dark was to swing the oscilloscope into position, check our power connections, and pick up our tools. In the darkness, the 150-watt bulb created an effect like a searchlight because of the parabolic mirror. We put the spark gap in its place. Though this was a relatively small light source, the efficient focusing of the parabolic mirrors gave us a bluish trace on the screen at the receiving end which was sufficiently strong for our photocell. So we made our connections and switched on the oscilloscope. With the long path blocked once more, we adjusted our oscilloscope. The short path was triggering the scope perfectly and giving us a good blip with a clearly defined peak. Then we took away the baffle, and sure enough, the long path brought in a good, strong signal. As you'd expect, this blip looked very much like the other. So, for our distance of 300 meters, the time measurement, the separation of our two peaks, was 5 divisions, plus or minus perhaps 1 or 2/10 of a division. This was just about 1 microsecond, as we had anticipated. The principal limiting factor on the accuracy and precision of our measurement of the velocity of light was the resolution of the signals on the cathode ray tube. And of course, the accuracy also depended on the exactness of our distance measurement and on the calibration of our electronic clock. But you have seen that we were able, with relatively modest equipment, to make a fair stab at a measurement of the velocity of light in air. Now it remains for us to discover whether light travels at a different speed in water, and if so, what difference in speed there is. The first measurements of the velocity of light in two different media, made over a century ago, caused scientists to alter radically their theories on the nature of light. So it will be worth our while to make this measurement for ourselves. In this experiment, the basic pattern of the light travel is from a light source here to one corner of our work area, where we have a very small plane mirror mounted on a shaft which we can rotate. This movable mirror reflects the light toward the opposite corner of our work area, where it is caught by each of two plane mirrors. One of those plane mirrors is submerged in water at the end of a trough. The other stands in the air beside the trough. These mirrors reflect the beams they catch back to the small movable mirror. And in turn, this rotating mirror reflects those light beams back to the source. The small mirror, which we can cause to revolve, is mounted here at the top of this black casing. Now here you can see the two different light paths, the one for air and the one for water. The air path leads to the distant mirror on the right. The water path is to the left, traveling down the trough. It enters the water trough by means of mirrors arranged as a sort of periscope. Then it travels through the distilled water to a plane mirror at the other end, back to the periscope, and so back to the revolving mirror. The part of the paths between the source and the revolving mirror and back are, of course, common to both light paths. The light source for our experiment is a carbon arc, which delivers a strong light focused on the revolving mirror. Between the light source and the revolving mirror, we have a mask which cuts off all but a narrow slit of intense light. When this narrow beam of light strikes the revolving mirror, it is reflected away as a pencil beam which scans through an arc about the pivot point. As the mirror revolves, it throws the reflection much like a searchlight scanning across the sky. Now, the only fragments of this scanning beam which concern us are those fragments which are returned as the pencil beam scans across the mirrors at the far end of the path. The distant mirrors reflect the fragments or pulses back to the revolving mirror, and the revolving mirror in turn directs them back toward the source. Now, for the moment, let's consider just the air path. During the time that the pulses are in transit to the distant mirror and back, the revolving mirror will turn through a small angle, and thus the return beam, reflected from the revolving mirror into the source, will be displaced through a small angle, an angle dependent on the time of transit and on the speed of rotation of the mirror. Now, we know that light travels at a tremendous speed, so it is clear that if we are going to get a deflection of the return beam, which is large enough to be observed, we will have to be prepared to rotate our mirror at a very high speed. To accomplish this, we have mounted our mirror on the shaft of a motor which can be revved up to 500 revolutions per second. That's 30,000 revolutions per minute. This is our variable transformer here. I'll turn up the speed of the motor while you listen to the pitch of the sound. Sounds like a sewing machine? Like a vacuum cleaner? Like a power sander? But listen to how much higher I can turn up the speed yet. So you see we have a very high speed available. We shall see whether it is enough to shift the return image of the slit away from its point of departure. Now, it's obvious that we need some way of observing our return beam to see whether it has moved or not. To solve this problem, we have introduced a half-silvered mirror here at a 45-degree angle. About half the light from the source will pass through it on its way to the rotating mirror, the other half being dissipated off to this side. On its return course, half the light will pass through to the source, but the other half will be reflected onto a small scale in our viewing device. In this pattern of light paths, we have had to introduce lenses to focus and control our light intensity. A card over this lens will block the water path temporarily, so that to start with, we will be using the air path only. Now we are ready to make our first observation. I will start the rotating mirror. Note where the light image appears when our mirror is revolving slowly. Even speeds up to 80 or 100 revolutions per second produce no apparent displacement of the image. But watch what happens as I increase the speed still further. Notice how the image is being displaced to the right. At a speed of 500 revolutions per second, it has moved about 2.5 divisions on our scale. With full knowledge of the distances, angles, speed of rotation of the mirror, we could calibrate our scale so as to read off directly the time of travel, as we did in the other experiment, and thus calculate the speed of light in air. But our concern here is to compare the speed of light in two different media, air and water. And we've arranged our viewing device so that the pencil which has traveled entirely through the air will appear primarily above the horizontal line on the scale. Now let's remove the obstruction on the water path so that we can observe both paths at once. The pencil which has traveled through the water will appear primarily below the horizontal line. Here is the way the water pencil will look. And here is the air pencil again. Water, air. Now you can see both pencils at once. The mirror is revolving slowly, and the traces are in their zero position. For our first comparison, we have set the distant mirrors at exactly the same distance from the rotating mirror. Now, will the two traces on our scale keep step with each other as I increase the speed of rotation? That would imply that the time of travel over the two paths is the same. Let's watch the scale. What do you see? The air pencil has assumed the same position as before, but the water pencil, that's the lower one, you remember, has moved out past it. The relative position of these two traces indicates that the pencil which traveled through the water took a good deal longer to return than the other. The speed of light, then, in water is slower than it is in air. To determine how much slower, we have gradually lengthened the air path until the two traces coincide. Now, with this longer air path, let's observe the scale again as I increase the speed of rotation. The two traces keep step all the way. They're both there, air and water. With this longer air path, then, the time of travel is the same. Now we've measured the relative length of these two paths. The distance the light travels up to this point and back through the air is, of course, common to both paths. But from this point onward, the length of the round-trip path in the water is 18.8 meters, and in the air, 25.5 meters, a ratio of about 3 to 4. So you can see that light travels considerably more slowly in water than it does in air. Indeed, just about 3/4 as fast. In your work, you have found that the index of refraction for light traveling from air into water is 4/3. Is there any connection between the index of refraction and our measurement? Or is the agreement just a coincidence?